Today we're going to talk about machine learning, and specifically we're going to look at a machine learning method known as random forest. Before we begin, let's load some packages that we'll need today. We'll mostly be working with a package called scikit-learn, abbreviated as sklearn. We're going to load a bunch of things from this package. We'll also be using NumPy and pandas as well as matplotlib. Finally, we're going to use a special package called graphviz. I will note that this package may take some extra steps to install. If you have trouble installing it, don't worry about it. We're just going to use it to look at a particular graph during today, and you'll be able to see the graph in the video. So what is machine learning? You may have heard this term before, and it's a term from computer science that describes a set of algorithms that are developed from data rather than being programmed with explicit rules. So machine learning relies on statistical approaches to make models from data. As a result, there's a substantial overlap between statistical modeling and machine learning. In the end, it doesn't really matter what you call the approach. A lot of the terminology that's used between the different fields is different, but under the hood, it's really basically the same stuff. So it doesn't really matter what you call it. If you prefer to call it statistical modeling, then great. If you like the term machine learning, that's fine as well. Here we're going to use, as I mentioned, a machine learning approach called random forest, which was developed in the 1990s. And we're going to use a public data set called the IRIS data set to explore this random forest method. And the IRIS data set contains 4 different flower measurements, so petal length, petal width, sepal length, and sepal width. So those are different parts of the flower and measurements of those for 50 samples each of 3 different iris species. It was originally collected by British botanist Edgar Anderson, and it was first published in 1936 by famed geneticist and statistician Sir Ronald Fisher. And so today we're going to be using the scikit-learn package, as I mentioned, to conduct a random forest analysis. And conveniently, the IRIS dataset is actually built into this package, so we can just load it directly. So let's do that. So we're going to load this. And let me go back and actually import these packages. Okay, so the packages are imported. And I will load the data set. Okay, so now our data set is loaded. And so what we're going to do first is split our data into 2 subsets. So we will use a training and a testing subset. And the training subset we'll use to fit the model, and then we'll use the testing subset to evaluate the performance of the model. And so that begs the question, how much of the data should we use in each subset? And there really isn't any one correct answer. Typically, we want as much data as possible to train the model, but we also need a large enough test set so that it is an accurate representation of the population we're interested in making predictions on, in this case, irises of these 3 particular species. And so for this example, we're going to start with a train test split of 75% of the data for training and 25% for testing. But there really is no one right answer for how much data you should use. So first thing we're going to do is because we're going to be randomly selecting some of the data, we're going to set the random seed, and what that will do is allow us to generate reproducible random numbers. And so we should all get the same results. And so what we'll do is first set the random seed using NumPy, so np.random.seed, and let's use 29 as our random seed. Okay, so Now let's define what our features are. So features are the data that we're going to use to make predictions. And so in this case, our features are the sepal length, sepal width, petal length, and petal width. And so this is our X data. So our X data is going to be from this iris data set, and it's just labeled as data. And conveniently, the data is already formatted for us, so we don't have to do that today. So now we're going to define the labels for each class. So these are the names of the species, and we've coded them as 0, 1, and 2. And again, this data is already formatted for us. So here we have our Y data. This is what we're going to try to predict or classify using the features. And now finally, let's next set a percentage of the data to use for training. So this is going to be our train percent. And we said we were going to use 75% of the data for training. Okay, so now that we have set these variables, we need to create our training and testing subsets. And so to do that, we will have define our train, a variable, we'll call it train, and we're going to use numpy to select random choice, so choosing, and we'll choose between true and false. So basically we're choosing whether to include a particular data point in the training set or not to include it in the training set. And we're going to have the size of this array that we're making, that's either true or false, is going to be the same length as our data. And for each measurement, we're going to give it the probability of in getting true will be our train percentage. So basically, each data point will have a 75% chance of having the value true, so being included in the training data set. And it will have, therefore, 1 minus the train percentage, or a 25% chance of being included in the testing data set. Okay, so this is our train. And so this is going to give us an array of true and false values, and we can use that then to subset our data. And we also want to create a testing subset. So we'll also create a testing array, which is just all of the data points that are not in the training array. So if it was true in this train array, meaning that it was included in the training set, it should be false, meaning that it's not included in the testing set. And there's a convenient function in numpy to invert a true-false array. So we're going to use that. So np.invert, and we'll invert this training. That will be our testing set. Okay, so now we actually have to use those to subset the data. So we'll make our X data for training. So we'll call it X train. It's just the X data. That's with selecting the true value, so just the train. And then we'll do that for the Y train. It's just going to be Y data. Again, selecting only the values that were true. So Y train. And now let's just do that for the testing set. So we've got X test is the X data, but this time we're only going to select the points that were in this testing set, so the ones not in the training set. And then Y test is going to be the Y data, the testing set. Okay, so we can run this, and now we've split the data into training and testing sets, so we can start developing our model. But before we jump into random forest, let's start by using a simpler classifier called a decision tree. So a decision tree works like a flow chart. Each node in this flow chart is a condition that can be answered as true or false. And so decision trees can actually be used for both classification or regression. And today we're going to be classifying things. We're going to be classifying data points as one of 3 different species of iris based on those 4 flower traits. And so the first thing to do is we're going to define our classifier. So our decision tree classifier, and we're going to use the sklearn package. So we're going to use the decision tree classifier, and let's set some of the parameters. So we'll start with a max depth, and we'll get into what max depth means a little later. For now, let's just set it to 20, and we're going to set the random state because there's some random processes, random numbers that are going to be generated as part of this. I mean, because we want to have reproducible results, let's set the random state so we all get the same answer. We'll set that to 23 today. And finally, we're going to give it a criterion to decide how to evaluate its performance that it's going to use during training. So this is a criterion that it's going to try to minimize. So if you remember early in the semester when we talked about loss or the error that a model has, we're going to try to minimize that. And so here we're defining what criteria we're going to use to try to minimize when fitting the model. In this case, we're going to use criterion called Genie, the Genie index. And we'll talk about what the Genie index is in a minute. Okay, so we've now defined our classifier. So now we have to fit this model to our data. So the predicted y values, so these are the predicted classes for each point, are going to be the decision tree classifier, and we're going to fit it using the training data, so x train and y train. And now once we've fit it with our training data, we're going to use that model to predict the y values given the test x data. Okay, so now that we've made our model, let's evaluate how well it performs. So we can define, this is the score. So the score is going to be the accuracy score. So how well did it classify the test data? And there's a convenient function built right into scikit-learn called score. So decision tree classifier dot score, and we'll give it the test x data and the test y data. And so from this, it's going to compare how the predicted y values to the actual y values in the testing set, and tell us how many of them did it classify correctly. So let's see how well this worked. Oops, and I have a typo somewhere here. So there we are. So let's fix that. Okay, so there we go. So when we ran this model, you can see that it classified 97% of the points correctly. So out of 37 total points in the testing data set, so these are 37 different iris samples with a sepal length, a sepal width, a petal length, and a petal width. It mislabeled one of them. So that seems pretty good. And so let's dig a little deeper. We would like to see what's going on sort of under the hood. And we're going to do that by visualizing the decision tree that we use to make these classifications. And so this is where we're going to use that package GraphViz, which, like I said, it can be a little bit finicky to install. It depends a little bit on your system. So be happy to help you try to install it, but also don't worry about it too much, because we're just making a graph, and you'll be able to see the graph here. So we're going to define something called dot data, and this is going to be a special format of the decision tree, and then we're going to visualize that tree. So we'll use this tree.export graph viz function from this graph viz package, and we're going to give it our decision tree that we just made, and we're going to just visualize it here. So there is no out file, it's just set to none, and we're going to try to label this a little so it's easier to interpret. So we can define the feature names are just going to be the feature names, so that is the sepal length, sepal width, petal length, petal width. Those are our features. So the feature names from this iris data set. Okay, so feature names, and then the class names, those are the names of the different irises, are just the target names from the iris data set. So target names. So rather than using the 0, 1, 2 encoding that we use when actually building the model, we would like to print on our graph the name of each species so we can visualize it a little more clearly. Finally, we're going to fill in each little box that it's going to make, so we'll set fill to true. Okay, so now we've got defined this dot data, and give it a second to run. And this object is not really interpretable, so we're going to convert this to a graph that we can display and look at and hopefully understand. And so to do that, let's define a variable, we'll call it graph. We're going to use this graph viz package, and then from that we're going to give it this dot data object that we just created, and we're going to format it as a PNG image so we can actually look at this and interpret it. And let's just print out the graph. Okay, so it's a little cut off here. We won't worry about all the way to the end of the graph, but you can see that this is our decision tree that we made. So what you do is you start at the top, and you can see that you start with something. So in this case, we're going to start with one of our features called petal width. This is the petal width feature. We're going to ask a question about it. Is the petal width less than or equal to 0.7 centimeters? If it is, so if true, then we're going to call this sample an iris setosa. And if it's false, we'll proceed to the next step. And then we'll ask another question. Is the petal length less than 4.85 centimeters? If it is, so if true, then we ask another question, etc., till we get to the end, and we've defined, we've classified all of the points. And so you can see in each box we have something called the Genie Score. So I mentioned that before. That's a way of defining the error in the function. So in the tree. So basically, Genie is the probability that at a given node a sample is incorrectly classified. So a Genie score of 0 means that 100% of the samples were classified correctly at this node. So in this case, 33 of the samples out of 113 had a petal width less than 0.7 centimeters. And so that number of samples here was 33, and all 33 of those we classified as setosa were in fact iris setosa, and so the Genie score here is 0. So for those that are false, so it had a petal width that was greater than 0.7 centimeters. We asked next, is the petal length less than 4.85 centimeters? And if that was true, then we asked again, is the petal width less than 1.65 centimeters? And if that was the case, we called this class versicolor, but not all of the samples. So if we had a petal length less than or equal to 4.85 centimeters, we called that versicolor if that was true, but not all of them were true. So we had 39 samples that were less than or equal to 4.85 centimeters petal length, but 2 of those were the Virginica and 37 were versicolor. So then we had to ask this additional question about the petal width, and when we do that, then 36 of the samples meet those criteria, and all of them are versicolor. So again, the Genie for this node, this terminal node down here, is 0, but for here it was only 0.097. Okay, so that's just an example. And so one of the main advantages of these decision trees is they're easily interpretable. So just like we were looking, we can start at the top of the tree and we ask a question. In this case, we ask questions about the petal width. And if it's true, then we proceed to the next step. And if it's true, we assigned it to a particular class, and then otherwise we proceed to the next step. And we keep going until either this Genie index, which again is the probability that a sample is wrongly classified at a particular node, is 0, or we reach the maximum depth, so the maximum number of nodes which the user set. So in this case, we set our maximum depth to 20, so it will keep going until all of the Genie scores at the terminal nodes are 0, or we've reached this maximum depth of 20. And so why have a maximum depth parameter at all? And there's 2 main reasons. And so the first one is that decision trees can suffer from a particular problem where like a particular feature can be given excessive importance in the model, which results in something called overfitting, where the model fits the noise in the training set. So in the training set, all of the samples will keep making nodes and splitting the data until everything has a Genie score of 0. So everything's correctly classified. But really what was happening is at the end, we're making decisions based on parameters that aren't really generalizable. And so when we test it on a different data set, it's not going to perform very well. And so the deeper the tree is, the more nodes, the smaller the sample size at each node, the more likely you are to basically pick an arbitrary point that fits the training data set but doesn't generalize very well. So we can limit that by setting the max depth. Also, if you have a very big data set, by allowing the tree to grow really deep, it can take a lot of resources and be very slow to run. And so this is a way of limiting it and allowing it to hopefully run a little faster. And so go back for a second. Yeah, so as I was mentioning, an overfit model is a model that's too specific. So in the case of the decision tree, it had too many nodes, too many criteria, and we're fitting the noise in the training data rather than the underlying trend. And so the model doesn't generalize, and it performs poorly on the test data. Despite fitting the training data really well, it doesn't generalize. And so the opposite of an overfit model would be an underfit model. And so an underfit model also doesn't capture the underlying trend in the data, but because the model is too simple rather than the model being too complicated. And so this often results in poor performance on both the training and the testing data. And so one of the possible remedy to the drawbacks of decision trees is to use multiple decision trees together. And so this ensures that if we don't want any one feature to be given excessive importance, we can take a random subset of all the features and use that to build a tree, and then do that again with a different random subset. And then we'll classify each point, and then with all of our trees, and then we'll allow them to vote. So if the majority of the trees say that, sample 1 is an iris versicolor, then that's the classification we'll give it. But because we're using multiple trees that have different subsets of the features, no one feature is given too much importance. And so that can help with some of the problems of a decision tree. And this is what we call a random forest. So the forest because it's a forest of decision trees, and the random because we're randomly subsetting the features. So let's make a random forest for this data set. So first we'll define a random forest classifier, and again, random forest can be used for both classification and regression. Today we'll be using it just for classification. So random forest classifier, and we'll set that random state just so that we all get the same result, and we have to give it the number of trees in our forest. So this is n parameters called N Estimators, and let's just, for now, we'll set it to the default, which is 100. Okay, so now let's fit our model to our data set. So the predicted classes are going to be this random forest classifier model, and we're going to fit it with our training data, so X train and Y train, and then we'll use that model to predict the classes for the testing data. Okay, and so now that we've defined our model and fit our model, we need to evaluate how well it works. So the result of our model, so to speak, and we will get the score. So this is how well it performed on the testing data. So score, and then we'll give it the test data for X test and Y test. Okay, and then we'll just print out here, we're just printing out the accuracy. So let's look at that. So the model accuracy is 1, so it performed perfectly on the testing data. So on the testing data, there are 37 points, and it misclassified 0 of them. So great, so it performed slightly better than the decision tree. And so let's dig a little bit deeper and see, did it really help with this problem that decision trees have of giving certain features too much importance. And so we can actually dig deeper and look at the feature importance in each of the models. And so let's do that. So first, let's make a data frame that contains the feature importance, which is just a measure of basically how big of a reduction in that node impurity or the Genie score is attributed to each feature. And so that is a measure of how important that feature is. So we'll call that feature importance, and we'll make a data frame. And we'll have the random forest. Let's put that in quotes. Random forest classifier will be the random forest classifier feature importances, and then we'll have the decision tree classifier, and that will be the decision tree classifier feature importances. Okay, and now is our dictionary, and finally the index of this data frame is going to be those different feature names for so the sepal length, etc. So feature names. Okay, and now before we make this now that we've made this data frame, I should say, let's sort it by feature importance. We'll just sort it by the random forest one. Okay, so that is nice and ordered. So we'll sort the values, and by random forest, and we'll just do it, sort it ascending equals true, and we'll do that in place. So rather than making a new data frame, we'll just do it on this existing data frame. And I have a typo here, so let me fix that. There we go. Okay, so now that we've made this data frame, let's plot it and compare to see does the random forest model that we built actually solve this problem that decision trees can have. We are going to first make an index, and that's going to be the length of this feature importance data frame, and then we'll make bar plots, and so I've already have the code typed out here just to save a little bit of time, but hopefully you have some experience making bar plots before, so that's all we're doing here. Unfortunately this plot is a little bit cut off here, but let's at least look at the top two features here in both models, and when you run this yourself or in class, you'll be able to see the whole graph. So sorry about it being cut off a little, but the longer the bar is, this is higher importance. And we can see that the decision tree gives a lot of importance to this particular feature, petal width, whereas the random forest is a little bit more balanced. And so is a more balanced mix of important features. And so that's exactly what we thought would happen. The decision tree has this problem where some features are given too much importance. And that might explain why the random forest model seemed to perform a little better. And so up until now, we've just been using default parameters, but there are actually a number of parameters that can influence the performance of a random forest, such as the number of trees in that forest. So we just used the default 100, but we didn't really have a good reason to use that number other than just a common number, and it's a sensible default, but it's not necessarily the best value. And so these parameters are called hyperparameters, and we can potentially make our model a lot more accurate by adjusting these to our data set. And so the best way to find the optimal values for these hyperparameters is just through trial and error. But since there's an infinite number of possible values, so we could have any number of trees, for example, we're going to have to use an algorithm to sample the possible parameter space. And so we're going to use a method called a grid search. So basically we're going to give it a range of parameters to search through, and then it's going to select parameters at different intervals in that range and run the model and see which one performs the best. So before we run our grid search, let's briefly go over some of the hyperparameters for a random forest model. So the first one is this N Estimators, which is just the number of decision trees we build in the forest. And then the second one here is max features. So this is the maximum number of features to examine when deciding how to best split a particular node. So we could look at all of the features. So in this case, there were only 4 features, but oftentimes we have thousands or even tens to hundreds of thousands of features. So just looking at all of them might not be the best approach. And so we have different values. So there's the auto, which is just equal to the square root of the number of features. We can use log 2, which is the log base 2 of the number of features. Or we can just give it a fraction, which represents the proportion of features to include. So in this case, we can use try 20%. So we'll just try these 3 different ways of looking at the maximum number of features to examine at any particular node. And we'll see which one works the best. And then the third one is that maximum depth, which we talked a little bit about. So this is the maximum number of nodes in a given tree. So if we set it to none, then we can keep adding new nodes until the Genie index is equal to 0. Or we have fewer samples at a node than set by this other parameter, min samples split. So the min sample split is just the minimum number of samples required at each node split. So if the min samples split is 2, then for an internal node in this tree, we have to have at least 2 samples in order to split the node, for example. And then we have this related parameter, the min samples leaf, which is the minimum samples required at each terminal or leaf node. So this might be a different parameter rather than an internal node. This is one of the terminal or end nodes. So if we had 1 as this, set this parameter to 1, for example, then we're saying that at every terminal node where we're making a classification, you have to have at least 1 sample. If we set it to 10, you'd have to have at least 10 samples. Then, for example, the last parameter that we'll talk about is called bootstrap. So if it's true, we're going to use a random subset of all the samples to build each tree. Otherwise, we can use the entire data set to build every tree. Okay, so now that we've talked a little bit about what the hyperparameters are, let's try to set up this grid search. And so first we're going to set up the N Estimators. So we're setting up here, what we're doing is setting up the range of values to search over to find the best hyperparameters for our model. So for N Estimators, we're going to use something called a list comprehension to make a list of values to search through. So we're just going to take an integer because you have to have an integer number of trees. You can't have a half of a tree. Int x or x in, and we're going to use this function np_lin space, which is just going to give us an evenly spaced range of numbers over a particular range. So np_lin space, and let's just say we'll start at 25, so that'd be starting at 25 trees, and stop, we'll say 500 trees for this example, and we'll go by tens. So what we're doing is we're going to get a range, an evenly spaced range of integers between 25 and 500. And then we're going to search through that to find the best number of trees for our data set. Okay, so then of our max features, and we'll define the different methods for calculating that. So we've got auto, which you might remember is just the square root. We've got log 2, and we'll give it also just a fraction, so 20% of the features. So this is the number of features to consider when making a split at any particular node. Okay, so now we're going to set this max depth, so the maximum number of nodes in a given tree. And again, we'll use a list comprehension. So this again has to be an integer because we can't have a fractional node. X in we'll use the linspace function again. So here we'll start at 10, go to say 110. So these are reasonable parameter values, but again, you can play with the parameter space to search over, and there is no one right answer. And here we can go by 11s. Okay, so that's the max depth, but before we're done with max depth, if you remember that we can also have a tree that we're not restricting the depth of the tree. We're just saying keep building the nodes until you have a Genie score of 0. And so that would be max depth set to none. So we'll just add that to this list we just created. So max depth, and we will append to the max depth none. Okay, so max depth, and now we will set the min samples at a split. So again, this is an internal node. So we'll just give it a few values to try. This isn't that big of a data set, so we can try, say, 2. So at least 2 at an internal node. 5, 10. Again, like, you can play with these parameters, the space that we're searching over. Okay, so then we have the minimum number of samples required at each leaf node. So this is similar, but this is the terminal node. So we'll define min samples leaf, and we'll set that here. We can have 1, so we can minimum just 1 sample that we're classifying, 2 or 4. And finally, the method for selecting trees, that's whether to use the bootstrapping, where we just have a sample, or should we use the whole data set. So this can be either true or false. Okay, so now we'll make a dictionary that contains all of our grid parameters. And I've written it out already just to save a little bit of time. So I'll just paste that in here. Okay, so we've got our different parameters and stored it in a dictionary. So now we're going to run this grid search and find what are the optimal values. So first, let's just define random forest classifier, because that's what we're going to be doing a grid search on. So now we're going to do a random grid search. So randomized search CV. So this is stands for cross validation, which we'll talk a little bit more about what cross validation is in a minute. And we're going to use this random forest as our estimator. And then we have the range of parameters to search over. It's just this random grid that we gave it. And we're going to try this just for today. We'll use 100 iterations. So it's going to try 100 different combinations of parameters. So we're going to do 3 cross validations. So this is a way of testing the performance of the model, and we'll describe what that is exactly in a little bit more detail in a minute, but we'll just set it to 3 for now. And finally, we're going to set the verbosity. So that's just setting how much information it prints out to us on the screen. And we'll set the random state. So just so we get reproducible results, let's set it to 29 again. and then I'm going to set this n jobs parameter -2. So all this is saying is to use, by setting it to -2, use all of the processors on my computer except one to do this fitting. And it is unfortunately not behaving today, but let's just roll with it. So and we'll fit this data. So we're basically just running the grid search, and we're going to use the training data. So we're going to run all the grid search. We're going to do 100 iterations with our different parameters and see, based on those 100 different combinations of parameters, which one performs the best on our training data. So let's run that. So now you can see what we're doing. So it's going to take a minute to run because it has to do 100 different iterations. Okay, so but there's a relatively small data set, so it's already done. So that's great, and I think it's done. Okay, all right. So now that we've tuned the parameters, let's define a model, a random forest classifier model, using our tuned parameters. So our tuned hyperparameters are just the random forest random. That was our grid search and the best parameters. So let's make a new random forest classifier. We'll call it tune because we've tuned the hyperparameters. So random forest classifier, and we're going to set all of these. So N estimators will just be the N estimators from our estimators that we chose using the grid search. We'll do that for each of these parameters. So I'm just going to, I've written them out already. I'm just going to paste them in here to save some typing. Okay, so we're just using the parameters that we've chosen, and let's print them out so we can see what are the optimal parameters that we've chosen here. What you can see is here it's chosen to use 25 trees, minimum of 5 samples at a split, minimum of 4 samples at a terminal node. It's using this log2 method. The max depth is set to 30, and it's using bootstrapping. If you run this again, because it's a random search through the parameter space, and we didn't cover the whole parameter space, it may give you a different result. So if your hyperparameters look a little bit different than mine, don't worry about it too much, because this isn't a perfect, this isn't defined exactly. We're not going to find the optimal parameter. And if you were building a model for your own research, we'd probably spend a little bit more time searching through parameter space to hopefully really hone in on what those optimal parameters are. Now we can compare our models. So we'd like to compare the tuned model and the untuned model. And I've alluded to this a little bit before, but until now we've just been looking at the accuracy on one test set. But a more accurate way to do this is to compare the model accuracy across several different permutations of test and train sets. And so in this case we can use, so doing that is called cross-validation. And so in this case we can do 5-fold cross-validation. So that means we're going to take 5 different sets. And so for this one, each set will have 25% of the data held out for testing. and 75% will be used to train the model, but it's going to pick a different 75% each time. And then we can evaluate the average accuracy across those 5 sets. And we'll do that both for the tuned and untuned model. So first, let's define the method to use for cross-validation. And there are several different options, and we won't go into them too much today, but in this case we'll use this shuffle split method, which has the advantage of allowing us to define the test size and number of splits without it being so we can define both the number of splits and the testing size, and it will be relatively computationally efficient. So we're just use this method for today, but there are other methods. So we'll use 5 splits, and the test size is going to be 0.25, so 25%. And let's again set the random state. In this case, we'll set it equal to 27. So let's evaluate the tuned model first. So our tuned model result is, and we'll use this function called cross-val score to run the cross-validation. So we'll give it our tuned model, and we'll use the training data, so X train and then Y train, and we'll set this cross-validation parameter to this, which we just set over here. And now let's do the same thing, but for the untuned model. Result is going to be cross-validation score for just that original random forest classifier that we didn't tune. Use the same training data, train, and the same cross-validation method. Okay, so let's run that. So it takes a second to run, and now that it's run, let's just see what the results are. So we're just going to print out the accuracy for the tuned model and the accuracy for the untuned model, which is just the average accuracy for each of those 5 different runs of the model. And so you can see in this case the tuned model had 94% accuracy, 94.5, and this is 93.8% for the untuned. So it performs slightly better, but it's not a big difference. If you were to run this again with a different grid search or use slightly different even train test splits, you might have a slightly different result, and that's okay. So this is more of a this isn't 100% precise, particularly with the grid search where we only looked at 100 different possible combinations of parameters out of really an infinite number. And so we might not have the optimal parameters yet. And so if you were doing this for your own research, you would probably want to look at a larger set of possible parameters and try to pick ones until you see that you're not improving the performance of the model anymore. Okay, and so that's all for today, and for the in-class activity you'll have a chance to apply some of the things you've learned about random forest to a real-world data set.